Hi, very warm good morning to all of you. Welcome to the 4Vision webinar series. Today we are having a webinar on advances in 3D optical profilers for high resolution 3D mapping. And the presenter is Dr. Yogesh Jairam. And I would like to take this opportunity to introduce Dr. Yogesh Jairam. He serves as a key accounts manager at Bruker Nano Surfaces, and he is responsible for application development and technical support of surface metrology and tribology instruments in India. His academic background was in solid state physics and material science. He obtained his PhD in KU Leuven, Belgium, on working linear and nonlinear optical effects in metal nanostructures. Prior joining to Bruker, Dr. Yogesh was a postdoctoral researcher in University of Toronto. He has published in over 15 peer-reviewed international journals, and he is also presented at many international conferences. Before handing over the session to Dr. Yogesh Jairam, I would like to request all the attendees, please, if you have any question and answers, we have a Q&A session at the right side of you, where you can type in your questions, and we will try to answer as many questions as possible. And if the time doesn't allow to answer all the questions, we will get back to you through mail. And please, all the attendees should be in mute mode so that the webinar will go smooth and peacefully. And with this, I would like to hand over the session to Dr. Yogesh. Dr. Yogesh, please take over.
Yeah, thanks, Raghav. Good morning, everyone. Thanks for the introduction, Dr. Raghav. So today I'm going to talk about the 3D optical profiler and what are the advances in this field, and we will look at certain uh, areas like orthopedics and 3D printing to look more closely into the things, right? So that's the concept for today. Before we start, yeah, so okay. Let me introduce a little bit about our company. Maybe many of you are familiar already. So it's a short history of Bruker. So founded in 1960, mainly we're doing NMR at that time. But over the years, we have developed several other product lines, including XRD, AFM, microscope, etc., etc. So today, the one that we are going to focus on is 3D optical profiler. Um, Bruker has been one of the leaders in innovation and in developing breakthrough products, right? So one of the things that we are always proud of is the amount of people we have dedicated for R&D on the patents that are generated, right, so far by Bruker. This just not only helps us be in the cutting edge and also address some of the key emerging problems in various fields, right? Okay. Um, so I represent the Bruker Nano Surface division. So our focus in terms of instrumentation is to do with understanding the surface, right? The nano level surface, which are becoming increasingly complex, right? So even if you take something as prosaic as like, your lenses that you wear, like glasses or something, the number of layers for anti-reflection coating, scratch protection, smudge protection, etc., etc., and maybe also you have some coating that prevents the blue light from entering, or reduce the intensity of it to um, make your viewing pleasurable of your computer screens, right? So there are many surfaces that we encounter every day, and each of them have a very complex, if you look very closely in it. And this is this is the main need or the driver to understand the surface better so that we can engineer them in a smarter way, in a better way that's more economical, but also at the same time improves the performance of different tools. Um, this has been done like different. There are different techniques available. So we have like atomic force microscope, which gives you atomic level resolutions in certain cases, and we have nano IR spectroscopy, which gives the not only the topography in 3D, but can also give you a chemical signature of the molecules, right? Like based on the vibration or the IR spectroscopy. And we also have tools like nanomechanical test tools to understand how the mechanical property of the surface is. Like it could be hardness, could be scratch resistance, could be modulus, etc. And then we also have certain characterization tools like what we are going to talk about, like the stylus and optical profilers. This will help us understand how the surface texture is, what's the topography, what's the roughness. Uh, these will affect not only aesthetic characteristics of your material, but also the functional properties, right? Could be like tribology, for example, uh, will have direct effect due to the change in surface texture and roughness. And that's what we are going to focus on today. Um, so if you look at the like different characterization techniques available, and then you put it in like this kind of like a graph. So we have talked about, so we have the AFM, we have the stylus profilers, we have the optical profilers, and you can see one axis you have the lateral resolution in the x-axis, on in the y-axis you have the height measurements, right? So this is the z and this is the xy, and if you want very high lateral resolution and very high Z resolution, then that means you're detecting very, very small particles or structures, then you are looking at the AFM, right? But for most engineered surfaces, like could be like mechanical surfaces, could be lenses, could be orthopedic, etc. You are mostly falling in this regime of the optical and stylus profiler, right? So stylus profiler, and you can see there is a big overlap in different techniques. There's a focus variation, there's white light interferometry, there is stylus profilers. So there is this big overlap here, and also overlaps with the SEM data. The key difference, of course, is the SEM, you get only 2D, whereas here you are going to get 3D data, right? And this is the region that attracts our attention today. Okay. Little bit about our optical profiler systems, specifically on the white light interferometry, which we will focus today. This is a product that was launched by a company originally called Vico, which was later acquired by Bruker, and over 35 years of experience, right? If I remember correctly, this is the first company to have a commercial white light interferometry product. And interferometry, the name itself is synonymous to very high resolution, right? So like anything you want to have very low tolerances in terms of measurements, we are relying on interferometry, right? Could be anything, from even like if you're looking like XY stage movements, very high resolution, you need interferometric stages. And that's why this technique, when combined in a form like a microscope, it gives you a great understanding in almost sub-nanometer levels even sometimes, right? And this has been adapted for different industries, from lab scale systems to like full blown like wafer with wafer handlers for like semiconductor industries. And we have some dedicated systems, well, just small snapshots here you can see for automotive industries, where you're dealing with larger heavier components than you might in a lab scale or in a semiconductor environment, right? So it's been adapted to different industries. So what is white light interferometry? So white light interferometry is basically you're doing interference pattern, and from the interference pattern, you are calculating the topography or the 3D nature of your surface, right? So what you need to start with, you need a light source. This is typically a LED source, and this light source you are sending to the sample, and on the way to the sample, some part of the light is sent to a reference mirror, which is just this small black dot you see here. This is a reference mirror. And there will be a path difference, right? So the light travel to the mirror and the light travel to the sample, there will be a path difference because of the sample roughness itself. So if I have also a flat mirror, then I will have no path difference, then I'm going to get a bright light in my camera. Because of this path difference, I'm going to get some kind of interference pattern, right? Something like this, for example, if that depending upon the kind of illumination you use. And from this interference pattern, we can calculate what is this topography is all about. And this is something like, like a contour maps that you would see in an atlas or something. So as long as you stay in the same contour line, you're not changing your altitude, right? So if you change from one contour to other, you're changing the altitude. And this is how the algorithm reads this kind of interference pattern, and you can get a very good data. So here is an example. So what we have here is like, say, like a surface, like a ball bearing, like a simple spherical surface. And as you move the objective down, you are changing your focal point, right? So that means the interference pattern shifts as you move, because the interference pattern happens only at the plane of focus, right? If it's outside the plane of focus, there will be no interference pattern. So, and you can see as you shift, and you can see the pattern shifts because of that. If you look at simple like a focus contrast, that's why the focus is also going to change, right? As you zoom, I mean, as you move your lens, your focal point is going to change. And from this, you can actually get the topography, right? So here we are using the interference change. In this case, you're just changing the focal, right? So you can get this focal variation kind of data, but here the resolution is much, much higher in terms of Z. And all of them ISO certified so that you can compare between different tools and also at different sites, right? Okay. So just to summarize the technique so far, so you look at it. So we have the resolution of this technology. So you can see here, uh, the vertical resolution is sub-nanometers, right? So this is one of the highest resolution techniques that's available. That's non-contact, right? Um, and you also have unmatched range. In that saying, the vertical you can have up to like some 10 millimeter, the height difference, and you can still capture it with the same nanometer resolutions, right? And independence from field of view or working distance. So what does that mean is that, so this, because we rely on the interference pattern and then we are calculating the surface, it is independent whether I use a 5x objective or a 50x objective, right? So we all know, like, to have a roughness, which is a statistical parameter, the larger the area, the better it is. And that means you want to use a smaller magnification uh, objective, right? Whereas if you use technique like confocal, well, this means a trade-off with the resolution. Whereas when we use the interferometry principle, there is no trade-off. So you can use a smaller magnification objective and still get this very high vertical resolution on your sample. The lateral resolution, this is the resolution in XY. What's the, what's how small gaps I can resolve in laterally. So this is basically limited by the Sparrow criteria, sometimes also called the diffraction criteria. This varies based on the objective. So you go for a higher magnification objective, you get a better lateral resolution. You can go down to zero point 0.3 microns, and we also have some special packages called equity, which through which you can even go down to like 100 nanometers lateral resolutions, right? In a simple setup. Uh, Very easy to operate. I will show you some video just to give you some feel for how the system is working, how you use it, how simple it is to use. And then we also have, for example, the very high metrology, right? Metrology basically means, yeah, it's a reference technique for vertical calibration. and also this is directly traceable as interferometry, right? So you can compare between calibrated sample, you can compare different things. So that's why we talk about the gauge repeatability, right? Um, some examples here, you can see, this is a silicon carbide mirror, right? The silicon carbide mirror is a very, very super polished surface, like sub-nanometers. And what I want to show you here is we did talk about, the measurement is independent, the resolution is independent of the objective. So you go from 2.5x to 115x objective, and you can see the 3D roughness you measure is very consistent, right? No matter you are changing the field of view, so you are going from several millimeter by millimeter to few tens of micron by tens of micron, and you can see the roughness you measure is consistent across the entire range, right? And another thing that also we talk about is the dynamic range, right? So we talked about the nanometer resolution, but also measuring very rough things. So here, so you have a print that's on a glass slide, so it's like the super frost, right? And you can image that with our optical profiler. The glass itself is very smooth, right? And the lettering, which is printed, which is rough compared to the glass surface, right? So if you look at this with a 5x objective, you can see the glass being blue, lower and very smooth, and then the print surface is very rough, right? And then you can actually look into it. So you can look, okay, if I'm only interested in the print, then I can see the roughness is about 1 micron, right? And whereas the glass slide, you can see the roughness is in nanometer. You can see same measurement in one single measurement, you can capture these very different dynamics, right? So you're looking at order of 3 magnitude difference, right? So a huge difference between the surface itself, and we can very nicely capture it, and also have a very nice integrated image to give you a whole picture, not picture in pieces alone, but a full picture as well. And this technique is widely applicable. So if you have rough and slopes like this scalpels, or you have like a very high dynamic range where you have like this conducting wires, metal wires, which are 100% reflective against background, which is almost absorptive like solar cells, and you see very high lateral resolution, submicron resolutions on this kind of grid patterns. And you can see in different shapes as well, right? Like you have the gears, you have this kind of spherical shapes. I think it's a part of an implant, and you also have different, indent on your sample, and you can capture that, right? So this one, and it's also insensitive to color. So you have a bright, shiny white metal against a matte black. It's insensitive, right? So you are measuring the lens, and you can, it's fully almost black, but you can still capture it very nicely, right? So that is the main concept here I wanted to highlight. Maybe what you can probably also infer from this lens and these kind of things, you can see uh, fully specular reflective surfaces, translucid surfaces, transparent surfaces. Yeah, you can capture different types of surfaces as well, right? Not only in roughness, but also in terms of the quality of the surface, in terms of reflectivity and other properties, right? Uh, so the white light interferometry, I just want to talk here. So this one we did talk a little bit. So you can see here also the dynamic range from millimeter step height to very, very smooth surfaces. And this is the cross hatch patterns in engines that you typically see, like a honing of the cylinders, right? And then you have different structures. So these are polymers, sapphire wafers, and diameter some structures, right? So fine structures on your sample, uh, right? So here you can also see the top surface of the oil. There is oil here, and then there is metal. And you can see the oil thickness map on your sample, right? And also if you focus on the bottom surface, then you can capture the surface roughness of the metal topography as well. Or similarly, you can see here, we have a coating here on top of a sample, which is have this nice kind of textures, right? All different reflective particles here. But you are interested in the coating on top and what is the roughness and how nice the coating is. And that's what we capture here. So you can see the captured image is only from the top surface, right? And it's unaffected by all these below reflective particles, right? Okay. Uh, just a brief summary of the system that we are focusing. So this is the tabletop system, has a sample size of 150 by 150 mm, up to 5 kg sample weight. So vertical resolution, sub-nanometers that we talk about, lateral resolutions, in sub-microns, right? And fully traceable results through interferometric principle. Yeah. So just give me a second, just 1 second. Yeah, sorry about that. We also have, yeah, talked about different applications briefly, but you can also see here is a bit of summary. So you have from optics, manufacturing, yeah, from roughness, finishing QA, QC, films coatings, semiconductors, CMP optimizations, bumps, redistributions, overlays, tribology, measuring the wear, the sketch characterizations, the durability, and also like the MEMS and sensors, like measuring critical dimensions, etching depth, roughness, and film thickness. Yeah. Okay. All right. So what's the new advances that we have bought in with this with the newer generation of the system, the ContourX 100 and 200 series? So now you have a larger camera. So you have now a 5 megapixel camera, and that also means you also have a larger field of view. So you see more things with higher lateral resolutions, right? And this also directly translates through faster stitching, right? So if you want to stitch a larger area than what you can capture in one single frame, then you can stitch multiple frames, and then you can do faster because you're capturing a larger area at every single time, right? We also have improved algorithms from our PSI. We have also introduced a new algorithm called USI, which improves the measurements fidelity, which means you can see the previous ones. You have certain fringe patterns, which are artifacts from measurements, which are now completely removed with the newer, better processing. And also we can capture higher dynamic ranges, right? So you have sub-nanometer roughnesses to very rough areas in the same sample, and we can capture them, right, in the same measurement. Yeah, so we have the metrology quality. We talked about it briefly now. So we have different algorithms, the PSI, the VSI. We also introduced a new algorithm called the USI, the Universal Scanning Interferometry, with very high repeatability and very high quality. You can see 1 sigma is about less than 0.04%, right? Um, we have a new analysis software which lets you do a better way of reporting, but also do different kinds of analysis, which were not possible previously. Maybe we will talk a little bit about it briefly later. And we also have a simpler GUI, or the graphical user interface, which lets anybody without any experience, maybe you can learn the system maybe 15 minutes flat, right? You can go from a novice to be able to measure your sample maybe in 10 to 15 minutes or so, right? Okay. When we talk about the ContourX, and we talked a lot about this repeatability, the resolution, etc., it's important that we benchmark these against the standards, right? So we benchmark it against a couple of different standards. So one is the roughness standards, for example, and you can see the calibrated data and the measured data and almost one to one, right? So it's, you can see compliant with the ISO aerial roughness measurements standards. And similarly for measuring, let's say, critical dimensions, like the radius linearity, right? So you can get these standard ball bearing kind of samples, and you can measure the radius of curvature, and you can correlate it with the calibrated value. And again, you can see is one to one, right? So very high um, metrological standards that's there now in this lab scale systems that you can use very easily, right? Um, we also introduced the new camera, but also this camera comes with a new improved way. So we have increased the pixels. So we have now a 5 megapixel detector. And we also running in 2 to 2 binning modes. This reduces the noise and also improves the sensitivity, right? So if you look, well, this is the previous generation camera and the new generation, you can see a larger image for sure. But also if you zoom in, for example, here you can see with the new camera, there is a better sensitivity, right? This is not just cramming pixels, but also we have changed how we are monitoring these pixels by having binning, 2x binning, 4x binning, etc. So then you can see a higher sensitivity on your sample as well. So the algorithms itself, so we do measure we do measure the interference pattern. This is what we capture, and this need to be translated into the surfaces, the 3D images that you see. So this goes through these algorithms like phase scanning interferometry or vertical scanning interferometry, and in traditionally there is always a gap. If your sample falls in between, you do not have really like an ideal technique to measure in. So you kind of have this, subpar data maybe in this region. And then with the new USI, you can bridge the gap. And similarly, also the background noise now falls down. So when you're doing USI mode, you can get very low noise. At the same time, have a much larger dynamic range, right? So if you look at different examples, so you have a VSI, a USI. So if you look at these different engineered surfaces from metal cutting, abrasive, etc. So 80% of your needs can be met by just using USI, which is just easier. For very rough samples, you can still rely on the VSI, which is also available with the system to do the measurements. Okay, some more examples. So uh, this is to show you from the large field of view to the submicron field of view. You can see a large coin. You can see some facial features that are present in this coin, right? And you can measure the roughness in millimeter length scales, and you can see the etched silicon pyramids like photovoltaics, in micron scale region, and all kinds of surfaces, right? So you have curved surfaces and stepped surfaces like this MEM structures, and high contrast surfaces, right? Like your high polished metal with rough silicon, etc. Right? Okay. So I have a small video. Let me see if it plays well. So this is just to show you how the measurement is done, right? So, okay. So you can see there are 4 different things that's running at the same time. It's just to give you a quick overview. You can see on the top, it's a machined metal surface. And then you have a own pad, ball bearings, and scotch tapes, right? You have different kinds of surfaces. And all the data that you see, the video you see, is a real-time recording, right? There's not speed up or anything. So you can see how quick it is from press start to get the data, right? 3D data, you can see here. It's very quick. And you can see that the dramatic differences, right, in the surfaces. So you can see here this ball bearing and this turn surfaces. Yeah. So it's all done with the same algorithm, so you don't need to change any parameter or anything. You put the sample and then press, right? So this one we did. So the workflow is simple. So number one, you select the objective that you want to do. Then you select the measurement setup. So how fast you want to measure, what's the speed, etc. What's the quality of the data you want? So high quality, low quality. I am telling the surface is smooth or rough, right? And then you can find the surface, which is like autofocus, right? So you find the surface, and then you start the measurement, and then you do the analysis, right? So it's very straightforward. So I said 15 minutes. You put your sample, you find the surface, and then you go, right? So here is the video with also I put this a small cut frame capture from the microscope itself. You can see on the bottom. So you have two the ball bearings and the polymer film reflective. This is like a scotch tape. You can see. Put the sample there, right? You put sample. You are just moving the objective now down, down, down. So you are actually not focusing. You just move down to a safe height, and then you ask him to find the surface. So he will automatically find the surface. And you can also see these very nice fringes. These are quite challenging to achieve, right? So maybe I pause a bit here. So this, you find the surfaces. So this one, like we talked about, the scotch tape is on top, which is what we want to measure. On bottom is what you see the circles or the patterns. This is not on the tape. This is actually below the surface, right? So these are very challenging to do it manually. And again, you see here this ball bearing, the fringes, the interference patterns is almost very difficult to spot, right? With the normal eye, may take a trained operator to judge that. But you can see he put there, and then in a few seconds, the system automatically find the surface, right? Okay, so let's see. Yeah, so then you just start the measurement. Well, now you change the, so okay, there's a different sample now. Sorry, there's some edit here. So you have similar concept for optical flat and the cylinder as well. So you have optical flat sample, and you have the cylinder samples here. Um, Again, the same concept. You put it, you bring the objective to a safe distance, then press find surface. The system will calibrate it and find the surface and adjust this to get this nice interference fringes, right? Okay. Yeah, there we go. So you can see also now you find the fringes for this cylinder sample as well, which is, yeah, quite difficult to spot even after it's done. Um, Again, now this is for two very different samples. So white pad, so very rough, like polishing pads, for example. And then you have like this very nice turned metal surface, and you are doing the same concept. So you bring the objective to a safe distance with respect to your sample, and then find the surface, right? Right. So to summarize this part, so we already see some good examples, right? Right, let me see. So you have very shiny samples like this ones, like the silicon carbide mirrors that we saw, or this like pads, cylinders, ball bearings, etc. Transparent films like scotch tapes, right? We can capture all this on the fine surface, or the autofocus will seamlessly work for every surface that you have. So you put your sample there, bring it to a safe distance, and then start the measurement. So this is just another short video to show you how simple the measurement is. So you can see the workflow. So even a non-expert can get the data. Uh, this again is a live time data, right? So there is no artificial forwarding or anything. So place the sample. So this kind of like this USB stick kind of sample, you place it there. You bring the objective to some safe distance, right? You are not really looking for focus. You just make sure that it doesn't hit anything, and then find the surface, click that button, then the system is automatically adjusting the intensity and then is moving up the objective to find the focal point and then optimize it to get the nice fringes, right? Okay. So now, yes, find this automatic fringe location. The intensity is set once again. Then you press the start measurement button. You can see the live video image, which is just a normal optical camera image. On the right side, you have the topography as it's being collected, right? You can see how nicely this is being collected on this sample. So about 120 micron vertical scan that's being done here. So what's minus 60 to 60 using the USI mode, and that's it. So you can see the data now being plotted. Yeah. So it's that simple to use the measurement, and you are still getting very high resolution data. I just want to talk a little bit about a few applications. How much time we have? Okay. Right. I think we should have a little bit more time, right? So we can go slow. So you can, this is a 3D printed polymer part. So these kind of 3D printed materials go through different steps as well. So when you print, you have this like the interdigits, right? So you're printing on layers, and then you would need to polish it and maybe apply some dye or paint or for aesthetic reasons or to prevent corrosion or whatever, right? So it goes through different post-processing steps after it's printed. It could be tumbling, blasting, chemical polishing, etc., etc. Um, to give a little bit example, so here we have this sample that's prepared specially for us by Hoffman Group, used on a stereolithography technique, right? And then you have basically each block is going through different processing, right? Each square you see is gone through different processing steps. And to have the data processing, all the blocks that we measure is with a 3 by 3 median filter, and we use a Gaussian high pass filter, zero order, and we use the ISO 4287 and ISO 25178 standards for roughness measurements, right? Um, the blocks that you see here, different ones go through different steps. So some of them are just with polish with grind with abrasive cloths, different grids like 120, 600 grids, and some of them go through like polishing block, like the diamond polishing, and some are polished through polishing pads and polishing cloth, and some are blasted, right? So you go from different kind of surface finishes now. So the blasting ones will of course will be much rougher compared to this very nice polishing pad and polishing cloth data, and you're going to get different kinds of finish from that. We will not look at all of them. I just want to show you just about one of the step process how it is done. So you can see the original sample with the glossy finish. You have this interdigits, right? Between the interdigit is very smooth. So this is a 3D printed surface. So you're building the layers one after the other. So between the layers is quite smooth. Then you do the blasting to get this matte finish appearance. So you have a ceramic blasting or a silicon blasting or aluminum blasting. And you can see here for like a small area, how smooth this one is, how rough it is, right? And then to understand the blasting process, to understand how it's finished, what the texture is, we can study these different S parameters like SDR or SDQ, and then also look at the micro texture by measuring the roughnesses, right? So you use a Gaussian regression filter, and then you can, with a different filter wavelengths, so let's say 0.8 to 0.08 millimeter, or less than 0.08 millimeter for roughness measurements, right? Um, this is very critical because, if you are painting or doing any other coating after this finishing process, it's all going to depend on this, right? If you have very different roughnesses, the painting or the finish is not going to look the same. Um, yeah, so just to give like a summary, so you can see here, you have the initial glossy surfaces with very, very low roughness, and then you have the ceramic, silicon, or aluminum blasting, and you can see that the aluminum blasting seems to give the best response. Um, the aluminum also, you need to know, is a little bit softer compared to the ceramic or the silicon particles you use to blast, right? And maybe that's one of the reason why that seems to give the better roughness or improve the texture a lot better than the harder materials like ceramic or silicon. Okay. A similar concept. This is for orthopedic substrates surfaces. Well, this is not, of course, 3D printer, but these are like casted surfaces or machine surfaces. You can uh, see the raw casting surface, and then you have different steps. So you have grinding, you have finish one, and then you have final buffing, polishing. You know, these are very need to be highly controlled and highly repetitive. There are a lot of regulations. These go inside people body, right? And if it's too rough, or it can actually create more trouble. If it's too smooth, also it doesn't, enable the cell growth and doesn't let the body easily accept it. So it needs to have a correct kind of finish, and this can be done here. You can see these are much complex shapes than the one I showed you before, and you can still capture them, right? And that's the concept. Um, and we have the new VisionMap version 8 software. So it has a better reporting functions. So now you can generate like this nice PDF data, and if you're doing repeatedly the same measurement, this also makes it a lot easier. You can get the same part, and you can set some tolerances values and get alerts quickly when there is a fail. You also have access to a larger varieties of norms and standards, right, than before, and also more granular control in terms of how you set up these parameters, right? So it could be, for example, what's the filter wavelength, what's the lambda S filter, what's the lambda C filter, etc., etc. You can have this good control so that you not only make a good report or data one, but also comparable to other data published elsewhere, could be from your other factory sites or from other publications. As a large language support, especially in industries, is very important, right? Nowadays people are collaborating with different industries. Some are doing based in Germany. Maybe they prefer to have a German kind of data, or it's generated that way so that the technicians can understand it. And you have English and and Chinese and Korean, etc., etc. Right? Okay. Yeah, and also with this you can now get more applications, right? So you can now do like full optical range, full range PSDs. You can measure the sectional volumes of tribological, like a scratch. What's the maximum depth? What's the area of the hole, etc. And if you have a semiconductor, you can do the overlay calculations. You can rank the defects on your sample, right? So those kind of things. Um, yeah, of course, no tool is complete without the support or the help in getting the best out of the system. Um, in India, we have a local customer support team through Fovision. Many of you are aware of them. They have been helping us in both the sales and the after-sales support, installation, training, maintenance. We have a local application team through Bruker, and also we have application team in our Singapore lab to give you more advice, expert level advice. Organize several workshops and seminars. I think many of you are maybe aware already of our online training courses. This we do conduct periodically, sometimes general like this one, but sometimes more specific for a particular application or a particular kind of measurements. And we also have online help desk to support the users anytime, right? So those kind of things. So to conclude, yeah, you get accurate results quickly, a wider field of view, higher lateral resolution with the newer generation ContourX systems, means faster throughputs in stitching, and high fidelity data, high dynamic range data, very high metrology quality, and have enhanced reporting analysis capabilities, and a GUI which makes it easier to do the measurement and analyze in a quicker way, right? Um, this is just also a portfolio of our products using the white light interferometry. So from the simple tabletop systems with automated tabletop systems to larger systems like maybe suitable for automotive, like large heavy samples, to like full integrated systems for like, semiconductor fabrications labs. So that's the different concepts. So that's all from my side. I can open the floor for questions. So I think you can leave your question in the chat window, or you can also, yeah, I think that's the better one. So you just leave your question on the chat window, then we can take the question and answer it. Um, if you want to write to us, you can also write to us at bns.asia@bruker.com. Then we can also answer the questions through that chat. So yeah, the floor is open for questions. Um, okay, so one of the questions that I receive is like, what's the best, the optimal objective to use for measurements, right? So this is a good question. So like, okay, let me see if I can show you the data here. Right, maybe this one. So when you are selecting the objective, of course, the vertical resolution is independent of the objective choice, right? So if you are going to choose objective, so it doesn't really matter what's the vertical resolution you need to do, but your objective will determine what is the lateral resolution you want to do. So if you are measuring roughnesses, right, and you want to use a particular kind of filter, which is like a common ISO filter, then it doesn't really matter because these filters are of much larger wavelength, and even our standard 5x 10x objective is fine. But maybe if you have very fine line widths, like you have a MEM structure, or you have like a, patterns which are very closely patterned surfaces or structures in there, then you might need to choose an objective which gives you a higher lateral resolution than the structure gap that you are trying to resolve. Yeah, so that's how you choose the objective. So it depends on the sample. So what are the necessary steps to calibrate an optical profiler? Okay, so also good question. So let me show you, this is the schematic of the objective, right? So all the things happen here. So this objective, you can see this is called the Mirov interferometric objective, and it has two plate beam splitters and a reference mirror. So these are all housed inside the objective. So this comes from the factory, right? You cannot do anything, tamper anything. So these are calibrated at site. So at the installation side, you will have calibration samples which are certified. So then you can use the certification to calibrate and periodically check. So from my experience, so there is not going to be a lot of drift or anything anywhere. It's not going to change. So once you have the calibrated objective from us, and you also calibrate it at the time of installation, this should hold for several years maybe, but you can get certified calibration samples to periodically check. And in case you see something moving or changing, you can recalibrate it on site. And this can be done pretty simply. So maybe I would recommend a calibration check once every 6 months. That should be sufficient. Yeah. Okay. Any other questions? Okay, so if you like to know the on-site calibration processes, I think we can take it offline. It depends upon your system. Also depends upon the warranty or the AMC support you have from us. So I will take it offline, and then discuss this separately with you. Yeah. So then we can discuss the details, right? Okay. If there's no further questions, I thank the audience and thank the organizers, the provisions. Yeah, so thank you very much. If you still have, yeah, sorry. If you still have more questions, you can drop an email. Let me put back the slide. All right, there you go. Yeah, you can leave a message at this email address. Yeah, thank you.
Thank you very much, Yogesh, for a wonderful presentation with good insight about the new system and advanced features and its capability for the metrology applications. And we would like to thank all the audience for spending their time on and attending this webinar. And with this, I would like to conclude the webinar. And once again, I am thanking one and all for your valuable participation. Thank you.